Let's see what happens to the momentum in case of a one-dimensional collision. Now for this, let's take these two interacting objects as one system. So let's say we are dealing with the A plus B system. Now on this system there are no external forces. So since F external is 0, there is no net external force, there are no individual external forces, nothing of any kind. The only interaction that happens here is between A and B, and these forces are internal forces of the system if I take A plus B as a system. So the net external force is 0, so therefore I can say that acceleration of center of mass should be 0, and if this is the case, then that implies that velocity of center of mass must be a constant. Now how can I write the expression for velocity of center of mass? So let me say that in a very general sense, before the collision, A was moving with a velocity UA and B was moving with a velocity UB, let us say. This was a situation before the collision. And after the collision, what happens is, maybe this guy A starts moving with a velocity VA and this guy B starts moving with a velocity VB, and the situation on the right is what happens after the collision. So what we can do is we can try to write down the expression for the velocity of center of mass before the collision and after the collision and equate them, because the velocity of center of mass should be a constant. So what do I get? I get MA UA plus MB UB divided by MA plus MB is equal to MA VA plus MB VB divided by MA plus MB, and you can throw up that MA plus MB here and you will get MA UA plus MB UB is equal to MA VA plus MB VB. Okay, cool. So this shows you that the total momentum of A and B before collision is equal to the total momentum of A and B after collision. In fact, the total momentum of A and B at any time during the collision will also be a constant, because the velocity of center of mass will always be a constant. So it's not just before and after, it's also during. So let us try to write this in words. Velocity of center of mass, or not velocity, let us say momentum of system before collision, that's the term on the left hand side here, is equal to the term on the right hand side is momentum of system after collision, and that is also equal to the momentum of system during collision. At any instant, and I'll put during in quotes, so that implies that I'm talking about the small time during which the objects are in actual contact with each other. So please keep in mind that the momentum will be always conserved, irrespective of whether I'm talking about third case or the second case or the first case. So you can have a perfectly inelastic collision, you can have an inelastic collision, you can have a perfectly elastic collision. Whatever happens, you can always try to conserve momentum. But we cannot say the same for energy. Now initially, if you look at this entire system, And let's, for the time being, ignore the changes in the gravitational PE, because let's say A and B are on a horizontal surface and they are going to interact on that horizontal surface. So if their heights above the ground are not going to change, then I can ignore that gravitational PE term. Fine. So what else can I talk about? I can probably talk about their kinetic energies, which they have by virtue of their velocities. So I'm talking about their Ks, okay. And I know that there will be deformations that A and B will suffer. So maybe I'm going to talk about their elastic potential energies. That's the energy of deformation. We know how springs work. So maybe if I think about the intermolecular bond as a spring, or maybe even better, if I think about the intermolecular bond as maybe elastic rods, right, then I can probably speak about their elastic PE also. So let's keep in mind that we are going to talk about kinetic energy of the blocks. So blocks have kinetic energy Ke, and blocks will also have, may also have elastic potential energy. Let me say EPE with the E capital. And there may be loss of energy sometimes. So we will see that also. So now when we have the initial configuration where A was moving with a velocity UA, and let us say B was initially moving with a velocity UB, at this point of time neither A nor B had any kind of deformation. So we can ignore this EPE contribution, and we can say that the total energy of the system is only kinetic energy. So at this point the total energy is kinetic before collision, the total energy is kinetic. So we have Ke of A plus Ke of B, that's the total initial energy. And during the collision, you know that some of this Ke will be lost. So what happens during the collision is that A deforms B and B in turn deforms A. Of course, the far side will not get deformed. So this is B and this guy is A. So some Ke is lost during collision. And when I say during, I'm only talking about the time when the two objects are in contact, during that time. So during collision, some Ke is definitely lost, because A and B do work in deforming each other. Okay, cool. What next? Now where does that Ke go? Now this Ke can go in two places. One, because the intermolecular bonds, we are trying to model the intermolecular bonds as probably springs, or better as elastic rods. So let's say we are going to treat intermolecular bonds as elastic rods. You know that a rod of steel, if it is stretched and then let go, it goes back into its original shape and size. If it is compressed and then let go, it goes back into its original shape and size, provided we are doing everything within its elastic limit. And maybe if we bend it, or if we take it, if we extend it maybe by a much larger amount, or if we compress it by a much larger amount than what is actually permissible, then there will be some deformations that will never be reversed. So that steel rod will be extended by a certain amount, or by or deformed by a certain amount, or maybe bent by a certain amount, and that will never undergo a reversal. So some energy will always be lost there. So these intermolecular bonds behave like that. They behave like elastic rods. So some energy may be used up in deforming them elastically, so that after they are being deformed, they regain back their original shape and size, but some energy can also go into giving them some kind of permanent deformation. So the loss in Ke here, let's write that loss in Ke is going to be stored as deformation, stored as energy of deformation, let us say, or elastic potential energy within the material volume of A and B, plus some amount of loss will be used to deform them permanently. Lost energy, so this energy is used up in breaking the intermolecular bonds, or altering the microscopic structure of the substance. So some amount of energy may be lost. Now what happens? So now if the shape and size are regained completely, let's go to the elastic case. So I go to this case where I'm talking about a perfectly elastic collision where the shape and size are regained completely. So if I see that the substances have regained their shape and size completely, then I know that finally there is no elastic P stored and there is no loss because there was no damage to the intermolecular structure of the objects. Then in that case, all that energy should finally be recovered in the form of kinetic energy. So there is a case where the shape and size are regained completely, then final elastic potential energy is 0 because there is no deformation in the substances. Initial elastic potential energy was also 0 and no loss of energy in causing permanent changes to the intermolecular structure. In such cases, Ke final is to be equal to Ke initial. So I can say that the total kinetic energy finally is equal to, in fact I don't even have to write that, this is enough. So the total final kinetic energy is equal to the total initial kinetic energy. But we should avoid saying that kinetic energy is conserved at every moment. No, it is conserved between the initial configuration and final configuration. But there will be some time in between where A and B would have undergone deformations. And there, at that point, some energy would be definitely in the form of elastic potential energy. So at that moment, Ke would have definitely gone down. So let's keep in mind that fact. So Ke finally is equal to Ke initially, but it's not equal to the Ke during the collision. So this is not true. During the collision. That is because during the collision there is definitely some amount of deformation, and so there is definitely some amount of kinetic energy that is lost. Now if I ask you what is that state in which the kinetic energy will be minimum, in what state will kinetic energy be minimum? That is clearly the state with the maximum elastic potential energy. It's the state with maximum elastic potential energy, and the state of maximum elastic energy will be the state of maximum deformation. So it is the state of maximum deformation. And you have to keep in mind that in the state of maximum deformation, the two objects were traveling with equal speeds, u and u each, and that was also equal to the velocity of center of mass. So that should remind you about that formula which I gave you in one of the classes, and that formula was kinetic energy of a system of particles. Kinetic energy of a system of particles in the ground frame is equal to kinetic energy of the same system of particles in the center of mass frame plus half times the total mass of system times velocity of center of mass whole square. So from this formula, I think we spoke about it that day also, that K in the ground frame will be minimum whenever K in the center of mass frame is 0. Now K in the center of mass frame will be 0. Ke in the center of mass frame is 0 if all particles are moving at the same velocity as the center of mass. So we should have been able to guess that from knowing this equation and from seeing this state of maximum deformation here, that at in this state, if the velocity of A is equal to the velocity of B, which is also equal to the velocity of center of mass of A and B, then this is the state in which the value of kinetic energy as found out from the ground frame is going to be least. And so it is in this state that some other form of energy is going to be maximum. Now we know that that other form of energy is the elastic potential energy, and that elastic potential energy will be later recovered as kinetic energy. But if they give you a sentence saying that Ke at all times is equal to the initial Ke, then you know that that is definitely wrong, because during the collision that Ke would have converted to elastic energy. So what next? Next is a case of in case of perfectly inelastic collision, or even just inelastic collision. You know that in both these cases now, because there is some residual deformation, and so there should be some kind of energy loss in deforming the substance permanently. Some energy would have been lost in breaking the intermolecular bonds and changing the intermolecular structure of the substance itself. So the final Ke will be less than initial Ke. So in case of perfectly inelastic collision or inelastic collision, Ke final is going to be less than Ke initial. So that's one conclusion that we can draw. In fact, now if I ask you, in which kind of collision do you think that the loss of kinetic energy will be maximum? So you know that there will be maximum loss of kinetic energy in those cases where the residual deformation is maximum, and the residual deformation is maximum in case of perfectly inelastic collision. So since in case of perfectly inelastic collision, since in perfectly inelastic collision the residual deformation is largest, therefore loss in kinetic energy is maximum in perfectly inelastic collision. So please keep this in mind. So if they ask you that two objects are interacting and they interact such that finally the loss of Ke is maximum, that phrase itself should help you understand that the objects have undergone perfectly inelastic collision.